So we're essentially this week going to be talking about exponents, but we have to finish up last week's topics, which were circles and distances. And then essentially it's all about exponents. And on Thursday, we'll be talking about polynomials. So we left off here. A circle is defined as the set of all points that are the same distance from a fixed point. This is what I wrote down. I drew the circle with this particular radius. So to understand this notion of a circle a little bit better, we need to know how to measure distances on this XY plane. This isn't really enough to assist us. So we need basically an algebraic expression, since this is not exactly that helpful. So let's consider 2 points, and we can draw a picture, a sketch here. Let's say we have X and Y. What is the distance between these 2 points here and here, let's say, with this point being X1, Y1, and this is X2, Y2. Well, we could draw essentially a triangle, 90-degree triangle, where this is your first point, X1, and this is your X2. Here, across, projected on this Y-axis, this is your Y1, and this one would be your Y2. So we see, or we could see, that this change in distance from, let's say, Y2 minus Y1 is equal to, let's call it B. And this change in distance, let me label this, is, let's say, call it X2 minus X1. Let's call that A. So what is this distance here from the points? Yeah, what is C? Right, exactly. Is there a formula for this? I'm trying to draw a triangle here at 90 degrees. So this is our B, and it's equal to Y squared. I'll rewrite it, Y1. And this is our A, X2 minus X1. And this is our C. And we know that this is called, thank you. So, perfect. Oops. Pythagorean theorem. So that is, and you've learned this probably from high school. Put up your hand, everyone, hopefully. Yes, perfect. So this is just going to be C squared is equal to A squared plus B squared. So we know this. We know this, hopefully. So let's relate the distance between 2 points to what we know. So we have essentially A is X squared minus 1, and B is Y squared minus 1. So this implies the C is equal to plus or minus square root, essentially A squared plus B squared. But this essentially, rearranging, is square root, and distance would be, that's a positive, so we could erase this minus here. Well, our A is X squared minus 1, so it's X squared minus 1 squared, and our b is y squared minus y1. And then we square it. So that is the formula for distance. So this is our distance formula. Let's call it d between these 2 points. We'll call it x1. Well, I'll just call it distance. So it's a very useful formula, especially in algebra, lots of different situations. But remember, we're talking about circles essentially. So we're trying to understand and come up with an expression for our circles using distance. So remember that a circle is just a set of points, all points, that are this equal distance from a fixed point. And we consider the fixed point, let's call it h and k. And if you want all the points, x and y, that are considered our distance away from like this point, hk, so that being the center, then you want something like this. But how do we get this particular formula? So it's just going to be, it's kind of like a transformation, which we talked about before. So we're subtracting, and what we did, so it's the distance formula. So x minus h, square it, plus y minus k squared, and then we take the square root, and that is our r is basically our c here. So we have like this point. You just square both sides, and we get our answer for a circle. So essentially, like these points, h and k, is the center of the circle. Sorry, I'm writing down here. R is our radius. Again, like this is our center. So this is our circle. At the point at HK with this radius R, and it consists of all the points X and Y, which satisfy this equation. This is why I'm writing it down, just so it's written, but you see it more clearly. So this is the key circle of equation, or formula for a circle. Okay, so find the equation of the circle with this particular center and radius 4, where r is equal to 4. And we're going to try to sketch the circle. So we know we want to put it in this essentially format. So this is the formula. We can extract, well, r equals 4, and we have the point -2 and 3, and that is equal to our h and our k. Okay. So that means our h is equal to -2 and our k is equal to 3. So essentially, we know, okay, we have x minus h is -2 plus y minus 3 squared is equal to our radius is 4. so 4 squared. And we could, a negative and negative, of course, make a positive. So we have this as our final answer. Now let's try to draw a sketch. I'll try my best. It's not easy drawing circles. So we know it's going to be centered at -2 and 3. So say so here. And then it has a radius of 4. So it'll be 1 unit down or 4 units down. So 1, 2, 3 down here. And over it'll be 1, 2 here, etc. And now we can connect those dots. So it's just 4 units all around the center. I'm gonna move my dot. It's a little off. And just try to draw the best circle you can draw. That's okay, I think. So this point, of course, is -2, 3. And this is our circle here. With this radius equal to 4 at the point -2 and 3. Perfect. Okay. So what about finding the radius and the center of a circle that looks something like this? So it's not in the same format as the circle that we just seen. How would we do this? Anyone have an idea? Well, we were talking about completing the square. We could put it into this format by doing the same trick. So let's write it down. So we could see like this part here, the beginning, we have 6, we have x's, and here we have y's. So we could use that trick of completing the square. So what would be the third term? Anyone? 6 divided by 2. Yeah. I'll just write it out the long way. 6 divided by 2. So we take this coefficient in front, divided by 2, 3 squared is 9. Yep. What about the next one? It would be -2, and I'm writing it out with the steps, the formula. So we take the coefficient, which is -b, divide it by 2, and then we square it for that term. Now we added some terms to the left-hand side. We have to add those same terms to the right-hand side. Okay, now it's in the format of completing a square. 6 divided by 2, you're correct, is 3 squared is 9. So this is going to be x plus 3 squared. This is going to be y minus 1 squared. Here on the right-hand side, this is 9 plus 1. And 9, 10, 16. So this is 16. We could write it in this, express it in this format, like there's a negative in front of h if we wish. So we could write it x minus 3 squared plus y minus 1 squared equals 4 squared. So now it's exactly in that format. So we can see that our h here is -3. Our, let's call it, our k here is 1 and our r is 4. So the center of the circle is at hk equals to -3, 1, and the radius is r equals 4. Everyone got that down? Just waiting on one more. Okay. So there's also ellipses. So circles relate very much to ellipses. And I'm going to try to do my best here to draw a circle. If we stretch horizontally, so basically we do a transformation, we can get this ellipse. It's sort of like this. Or we can also stretch a circle. This is, again, is my nice circle. That's actually not so bad. So this is an ellipse. So we can stretch it vertically. And this is also an ellipse. Okay, that's slightly angled. But I'm going to leave the unit here because there's other types of things too, like there's hyperbolas and various ways to transform a circle. I just wanted to mention this. Now, exponents. I would like to move on to the next unit. And I think this is a really important topic, exponents. If you take any additional courses in mathematics, calculus, anything with polynomials, you're going to see this. So we know that basically multiplication by a positive number is just a repeat of addition. So let's say you have 3 times 5. Well, we know that's going to be like, let's say 5 plus 5 plus 5. We know this. In the same way, let's say if we have 5 to the power 3, that is, this 3 is called the exponent. Let's see. This is the exponent. And this is the same as, so this is going to be 5 times 5 times 5. So this is 5 raised to a positive integer. It's just the repeated multiplication. And we know this, hopefully. This is a review, and you've seen this before. But it doesn't always have to be the integer it's raised to, doesn't always have to be like a positive number. And what you're raising it to doesn't always. So we're going to examine this. So this 4, this is positive, but this -2 over 5 it's not a positive number. So let's rewrite this. What would this be? -2 times 5, 4 times. You can see, okay, I put a negative up there. Let me put it out front. Doesn't really matter. So we know a negative and a negative make a positive. So like these will be positive. So this is going to be 2 times 2, 4, 5 times 5 is 25, times the next one is 4 times 25. And this is going to be 4 times 4 is 16. 25 times 25 is 625. What about an expression raised to a power or an exponent? Getting ahead of myself. So this is an expression. So we're going to rewrite this. This is going to be multiplying the expression basically 3 times. And you can work on it at the same time. So we can first multiply the first 2 brackets together. So that is basically FOIL, which you've done before. Then we have the last bracket. And then we can distribute and multiply everything together. So we've done something like this. So this is y to the power 3, multiplied by each one. 3y squared. And 9y and 27. Then what do we do? Yes? Right. And what am I looking for? How do you simplify? You're right. You add the like terms. Yeah, I think someone said it out there. So let's add the like terms together. So here we see like there's y squared and a y squared. And here we see y's. So 6, 7, 8, 9. Then we just add these. 27, y plus 27. Okay, So we know how to kind of now multiply expressions raised to exponents. So, and just remember to group the like terms, don't group unlike terms. That's a common mistake. So the following nice properties work essentially. So let's come up with like kind of a formula for y. So if x is a real number and m and n are positive integers, so we're first going to analyze the positive integer case, then we essentially get like this formula here. So x to the power m times x to the power n is equal to x to the power of the exponents added together. So let's quickly just see an example to the side. So for example, let's say you have 7 to the power 3 times 7 to the power, let's say 5. Well, we can add those exponents. So 5, 6, 7, 8, 8 here. And that's the equivalent of 7 to the power 3 plus 5. So I could give you all the formulas right away like that, but it's good just to take a second and understand how we get like these formulas. So why is this true, essentially? And I think it's actually worth doing for a second. So let's say you have x to the power m times x to the power n. That's the equivalent of x times x dot 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 x. Essentially, there's m terms of these, right? And this is multiplied by x to the power n. X times x. And there's n of these terms. So we have essentially x of these. And you're going to see there's m terms and n terms. So there's going to be m plus n terms in general. So this is why it's going to be x to the power m plus n. So this is why essentially this expression holds. And it's good, I think, always to try to find why they hold. Now let's look at this expression, because I rather like show you why it holds rather than just telling you this holds, right? So let's do the same thing, the same idea. X to the power m, and this is to the power n, and it's equal to x to the power m times n. So why is this? So the first power, we can write this out. This is x, m times. So there's m terms of them. And to the power n. And it's equal to x times m of these, n times of these. So let me try to draw this out a little bit more. So there's m of these and m of these. And each grouping has m of these n times. So the whole thing is n of x of these x's. So in total, there's going to be m times n terms, which is x to the power m times n. So we could do a little example to the side here. Suppose we have 5 to the power 2 to the power 3. So this is going to be 5 to the power 2 times 3. And you could see, well, 5 to the power 2 is 25 to the power 3. And we could, I don't know, use a 5 to the power, this would be 5 to the power 6. Now, these should be equal. And you could use a calculator. So I'll say use a calculator. To see that the expressions are equal. I'll just leave that for you to check. So it's also not difficult to show this one. I asked you to kind of like try to see why this holds. Oh, let me just circle this too. So just try to see why this holds. I'll leave this one for you to do, but we'll see an example. So basically, it's the product of x and y to the power, or to the exponent, is equal to x to the power n times y to the power n. And in an example of this, let's say you have 2 times 3 to the power 5. This is the same as distributing this like 5 into everything. So this would be the same as 2 to the power 5 times 3 to the power 5. So this would be 6 to the power 5. And this would be, and you can check that they're the same thing as this. So I'll say just check that they are equal. So these are equal. So I'll let you just check that with your calculator. Ask yourself, yes, are they equal? So what we did was we distributed that n into everything that is in these brackets, essentially. To the exponent. So far, we've only been concerned with these positive integer exponents only, right? We've only been looking at positive integers. We can also have the number 0 as an exponent, or even a negative number. So this is what we're going to look at. In any case, an expression of the form x to the power n is called the nth power of x. So what this means is, let's say you have x to the power 5. This would be, the correct words to say express this would be, this is the 5th power of x is how you would express it. So, and I was kind of saying those words instead of exponents. I was occasionally using power. I was saying that word because it's in my mind. I was getting ahead of myself. So you would say fifth power of x to the power exponent 5 is the same thing. Tomato, tomato. So x to the power 0 is actually defined. X to the power 0 is 1 as long as x does not equal to 0. Let's just color this in. Put it in a box because it's important and it comes up. We're going to kind of see why and understand this in a second. So this is very useful convection, actually, because the expression makes sense only if x to the power 0 is 1. And we get like this identity, essentially. So let's understand this a little bit further. I'll write this to the side. So x to the power n is the same as equivalent x to the power n plus 0. We know this, which is by the identity that we just have seen. It's x to the power n times x to the power 0. But from the previous identity, I think it was, just the last identity, which we just talked, x to the power n has to be equal to x to the power n only if x to the power 0 is by definition is equal to 1. So this only makes sense if, let's say, x to the power 0 is equal to 1. So it has to be x to the power 0 has to be equal to 1. Let's let me fix my 0. And again, this was from the identity. So let's just make a little side note. So from the previous identity. It was this identity here, or no, this adding one. Now, so again, like, what does this mean? So any number, so let's say 6 to the power 0, what does that equal? 1. What about 2 to the power 0? 1. What about -1/4 to the power 0? 1, right? So this is the point. Anything that's not 0 is to the power, anything that's not equal to the 0 to the power 0 is equal to 1. So remember that. However, what about 0 to the power 0? Yes, undefined. Why is this? So this isn't actually very meaningful. So this is a little exception to the rule. So suppose, for example, we had a 0 to the power k. Well, this would be like 0 k times. So that would be 0. And suppose like k does not equal 0. What about k to the power 0? Well, by definition, k to the power 0, we just said is anything is 1 if k does not equal to 0. So there's a confusion there, right? There's a contradiction. So this is why we have to say it's undefined. So yeah, it wouldn't really make sense. So you do have to watch that case. Now, we've been talking basically about positive exponents, power to the 0. We can do, of course, the same thing with negative integers, exponents that are negatives as well. So for example, x is not equal to 0, suppose, then x to the power negative n, by definition, it's this multiplicative inverse, which is the reciprocal, which we talked about before. And it's defined in this manner. So do not confuse it with inverses, which we were been also talking about. It's not the inverse, it's the reciprocal. So for example, 7 to the power negative 2 is equal to 1 over 7 to the power 2 by definition, which is equal to 1 over 49. So let's evaluate 4 to the negative 3. So 4 to the negative 3 is equal to, by definition, 1 over 4 to the power 3, which is equal to 4 to the power 3 is 64. Here, it's similar fashion. Just say equals to 1 over negative 5 over 4 to the power 4. But what do you notice here? The negative changes to a positive, and we put it on the denominator. Is the main idea. Now we compute this. Negative to the power 4 is positive. So 1 over, then 5 to the power 4 is 625. 4 to the power 4 is, oh, whoops, why did I write 4? No one corrected me. It's 2. There. 2. So 2 to the power 4 is 16. And we know how to flip these. So let's say you have A over B and C over D. This is the same as A times D divided by B times C. So we can just flip this to the top. This, our D comes up here. So this is 16 divided by 625. We've seen this before previously.